Okay, so let's look at finding the greatest common divisor and least common multiple using prime factorization method. Because once you have prime factorization, you can use it to find the least common multiple and the greatest common divisor. So let's say we're looking at the numbers 132 and 504. We want to use here they told us to use prime factorization method, the question stated. So let's find the prime factorization for that number first. So I see it's divisible by 2. It's going to be 2 times 100 divided by 2 is 50. 32 divided by 2 is 16. So together is 66, right? This is already prime. 66 is 2 times 33. 2 is already prime. 33 is 3 times 11. So that becomes now 133. Prime factorization would be 2 squared times 3 times 11. How about 504? We can split 2 times 252, right? 2 is already prime. This is not. 2 times 126. 2 times 63. 7 and 9. And 3 and 3. So I'm splitting into prime factors. So that means the prime factorization for that would be 2 to the power 3, because I have 3 factors of 2. Then 3 squared, 3 times 3, right? That would be those 2 3s, and 7. So now when I look let's start with greatest common divisor. Greatest common divisor meant that I can only list common prime factors, so 2 and 3. 11 and 7 will not be part of it, 2 and 3. And then I go with the smallest of the powers. If I see it appearing with 2 different powers, I go with the smaller. Well, 2 in both cases appeared with the power 2, so that's the power it goes with. But 3 goes with the smaller power, so it remains 3, not 3 squared. And so that's 4 times 3, or 12. Now, least common multiple, having prime factorization, I go with all the factors, even the one not common ones. So all the bases I see 2 in both of those prime factorizations, 2, 3, 7, and 11. If I see some prime base appearing more than once, like for example 2, this time I go with the bigger power. But in both cases, 2 appeared with the power 2, so there is no dilemma here. But in the case 3, I'll go with the bigger of the powers. And 7 and 11 appeared only once. Okay. And so that's going to be, I can use a calculator and calculate what that's going to be. And that's going to be 5,544. Right? Of course, I can always check, because the greatest common divisor times the least common multiple should be the same as the product of those two numbers. Okay? So if you multiply the greatest common divisor times the least common multiple, it should end up the same as the product of the two numbers, right? And you can check that they're the same on the calculator. Okay, so again, we're doing prime factorizations. So we first need to do the prime tree for 65. Let's say first thing that comes to my mind is 5 times 13. It's already, both of them are already prime. So 65 is just 5 times 13. 1690, well, I for sure 10 times 169, which is 13 times 13, Those are prime factors, but 10 is 2 and 5. We're done. So we have prime factorization for 1690 is 2 times 5 times 13 squared. So this time I'm gonna start, well, let's start the same. Greatest common divisor. So greatest common divisor of 65 and 1690 would be, I only select common bases, prime bases, so 5 and 13. And I go with, if there are two different powers, in case of 5, both times it appeared with power 1 only. But 13 appears with two different powers. Here power 1, and in the other one power 2. So I go with the smaller power, meaning power 1. So that's basically 5 times 13, or 65. So greatest common divisor of 65 and 1690 is actually 65 itself. What it means is that 65 is already a divisor of 1690. Now, least common multiple, using those prime factorizations as we have them already, then we put all the factors, not necessarily common. So for example, in this case, also we list 2, although even though 2 did not appear in the prime factorization of 65. And if we have two different powers, like in case of 13, the space appears with, then this time we're going with the bigger power. So that's gonna be 10 times 690, so that's 169, so that's gonna be 1690. And it does make sense, because if the greatest common divisor is 65, basically if 65 is a divisor of 1690, then that 1690 is already a multiple of 65, and therefore is the least common multiple. I meant to write here multiple. Okay. Okay, now we're going with the two numbers. Let's start with their prime factorization. 2 times 48, already prime. 4 times 12, 2 and 2, 3 and 4, and 4 is still not prime. It's going to be 2 and 2. So I have a prime factorization for 96 to be, I have 2 to the power 5, because I would have 2 times 2 times 2 times 2 times 2 5 times, and 3. Then let's look at 900. 900 I would write as 10 times 90, which is 2 and 5. 90 would be 9 and 10. 9 is 3 and 3. And 10 is 2 and 5. So prime factorization for 900, I will have 2 factors of 2 here, 2 factors of 5, and 2 factors of 3. And then finally 630. So let's say 10 times 63. 10 is 2 and 5. This branch is done. 63 is 7 times 9. 9 is not prime yet. It's 3 times 3. Notice that prime factorizations are not that difficult to find. Two factors of 3, 5, and 7. So when you now look at what's the least common, greatest common divisor, let's start with that. Now, what is the prime base that appears in all 3 factorizations? 2 and 3, because 5 does not appear in the first prime factorization of 96. You only look at common prime bases appearing in all 3 numbers. So that would be only 2 and 3. And now what power you go with for greatest common divisor is the smallest of the powers. So 2 will appear with power 1, meaning as 2. And 3 also with the just power 1, so as 3. Because other powers of 3 were 3 squared. Right? And you go with the smallest of the powers. So that's 6. Greatest common divisor, and I should list of what? Let me write it down. Greatest common divisor of those 3 numbers, 96, 900, and 630, ended up being 6. Now the least common multiple of all those numbers, again, if I look at the prime factorizations, which I already have, then this time I'm going to have to list all the factors that I see. So 2, 3, 5, and 7. And always with the biggest of the powers if they appear more than once. So 2 will go with the power 5. 3 will go with the power 2. 5 will go with the power 2. And 7 was just 7. And that's going to be a pretty big number. So we can calculate what that is on a calculator. And I got that to be 50,400. Okay. Okay, 108 and 360. Just to change, I know the problem here says use prime factorizations, but I'm going to go with prime divisors. Just changing just to do things a little bit, remind you of this another method. Remember, that's the one that you start dividing by first prime divisor. So 2, 5,480. You can still divide it, at least one of them by 2, actually both. You can still divide by 2 because 90 is divisible by 2 and 27 is not, so we'll stay the same. None of the numbers is divisible by 2 anymore. Next prime number in line is 3, and it does divide 27. So you use it. That's 9. And 45 divided by 3 will be 15. You still can divide by 3. That's going to give you 3 here and 5. You still can divide by 3, at least one of them. And 5 is not divisible by 3, so it will remain the same. Next prime number in line is 5. 1 is not divisible by 5, it stays the same, but 5 is divisible by 5, it will be 1. Once you end up with both 1s, you get your least common multiple. That was the method for the least common multiple of the two numbers to be, and you just list, you have 2 times 2 times 2. Or 2 to the power 3. Then 3 times 3 times 3, or 3 to the power 3 and 5. So that's 8 times 27 times 5. Okay, so you can multiply it and get number, I use the calculator, 1080. So if that's that, then you know that the greatest common divisor of the two numbers times the least common multiple has to be the same as the product of those two numbers. Okay. Okay, so you can now divide both sides by 1080. So that the greatest common divisor of those two numbers will be, and notice here if I divide both by 10, the 1 zeros will be simplified, and then you can also cancel common factor 108, so you'll end up with 36 will be your greatest common divisor. Okay. So let's look at this. And this was, I already mentioned that you have greatest common divisor of three numbers. And one of the approaches you can employ is to focus on a pair. And then whatever is greatest common divisor of that pair, you match it with the remaining number. So in this case, you choose a pair. I'm going to go with the pair 120 and 105 because they're kind of close to each other. So what's the greatest common divisor using Euclidean algorithm? The smaller of the two numbers, and then the remainder. Since 105 fits only once in 120, the remainder is 15. Then it's the greatest common divisor of 15, and then 15 fits actually how many times, guys? 7 times fully, meaning the remainder is 0. So that means that 15 is already the greatest common divisor because 15 divides 105. Okay, so now the greatest common divisor of those three numbers you started with is the greatest common divisor. The pair I chose 120 and 105 gave me greatest common divisor to be 15. So that's the number I didn't deal with yet, 75. And the greatest common divisors of the pair I did do. Okay. And then, well, 15 fits 5 times into 75, right? So 15 already is the greatest common divisor because it already divides. Okay. Let's look at the next one. It does appear the next one is the same, but here let's be sneaky about it. Remember, the greatest common divisor of two consecutive numbers, any two consecutive numbers, is 1. So now that means that the greatest common divisor of those three numbers is the same as the greatest common divisor of the number I set aside and didn't deal with, and the greatest common divisor of the pair I chose. But since they were consecutive numbers, that was 1. So now the greatest common divisor of those two numbers is 1. Right? And finally, let's do some applications. And I want you to recognize first whether we're looking for greatest common divisor or a multiple. Midas had 120 gold coins and 144 silver coins. He wants to place his gold coins and his silver coins in stacks so that there are the same number of coins in each stack. What is the greatest number of coins that he can place in each stack? So he basically tries to divide 120 into stacks of equal number, right? So that means that he's trying to find ways to divide 120 divisors for 120, right? He also wants to do the same for 144, but he wants to, for 120 and 144, he wants the stacks to match, right? So he wants to find the greatest common divisor of 120 and 144, right? Really. That will tell him how many coins in each stack he can create for both 120 and for 144, right? Of course, there will be less of those stacks for 120 than 144, right? So what's the greatest common divisor here of the two numbers? We're using Euclidean algorithm. It's the greatest common divisor. You grab the smaller number, and then what's the remainder? Well, 120 fits only once, and 144, the remainder will be 24. What's about that? 24 fits when we can grab a calculator and divide 120 by 24, and you're gonna get that the remainder is 0 because 24 times 5 is exactly 120. So if 24 already divides 120, then 24 is the greatest common divisor. So basically, he can create here 24 is the answer to this question, meaning he can put 24 coins for each. In case of 120, he would have to put 5 stacks of 24 coins, right? And in case of 140, he would have to put 6 stacks of 24 coins, right? And that answers the question. Now, the radio station gave away a discount coupon for every 12th and 13th caller. Every 20th caller received free concert tickets. Which caller was first to get both a coupon and a concert ticket? So here the question is, okay, so every 12th and 13th, right, receives the coupon, but every 20th receives a concert ticket. So people will call, and every multiple of 12, so already 12 callers, 12th gets the coupon, another 12, so 24th caller will get again coupon, and so on. So we're talking about multiples, right? And we want to know who will get first both concert ticket and the coupon. So we're talking about least common multiple of 12 and 20, but also possibly of 13 and 20, because 13th caller also might receive a coupon, right? And whichever of those two will be the smaller one, then that will be the first caller to receive both, right? So what's the least common multiple of 12 and 20th? Well, for 12, the prime, I'm going to go with prime factorization, is 2 times 6, or you could have gone 3 times 4, and 6 is 2 times 3. So 12, the prime factorization for 12 is 2 squared times 3, and for 20, I'm going to do 2 times 10, and 10 is 2 times 5. So for 20 is 2 squared times 5. So remember, if you're looking for a common multiple, then we record all the bases we see. I see 2, I see 3, I see 5. And not necessarily common, appearing in both prime factorizations. And then if it has had 2 different powers, I would go with the smaller of the powers, but 2 in both cases appeared in the power with the power 2. So there's no doubts here. So basically this, which is 4 times 15, which is 60, right? But what about in case of 13 and 20? Well, 13 is already prime, so 13 is its prime factorization, so that you don't do anything, right? It's already there. And 20 is 2 squared times 5. So if you look at least common multiple of 13 and 20, you record all prime bases you see, 2, 5, and 13. And if it appeared with 2 different powers, you would go with the bigger power. But here, we didn't have that problem. So that's 4 times 5, which is 20, times 13, which is 360, right? Sorry, 260. Either way, the first caller to receive both the coupon and the concert ticket would be the 60th caller, right? So 60th caller will be the first to receive both, right? Okay, and that is it.